Okay there. Hey guys. Um, this feels really weird because I feel like I'm talking to myself sitting in my apartment. Hopefully I'll get over that. Anyways, I hope you guys are doing good. I'm sorry we have to deal with all this. I've got plenty of Zions and B-dubs is walking distance from my apartment, so I'm good. But yeah, I hope y'all are doing well. This is really awkward. I'm sorry. Maybe I'll get used to it. I'm sure I will. I'm actually on a gaming headset, which hopefully that sounds fine. Anyways, okay. So today I want to do. We're going into simple harmonic motion and waves. Today I want to go kind of over a couple things. Well, the zero thing. Hopefully you read the wave equation notes. I posted those in the Google Classroom as well. Make sure you read those. Read the other ones too. There's some on simple harmonic motion. There's some on waves, which we'll actually probably talk more about next week. And then the spring system. But the wave equation notes are important. And I'll probably talk more about the actual wave equation a little bit next time. But the first thing we'll go over is kind of basic simple harmonic motion variables and their relations. Again, you can read that in the notes really. Next thing I want to do is talk about a vertical spring mass system. And then finally we'll do kind of energy of simple harmonic motion. Yeah, make sure you read those wave equation notes. And I might do I might cover like some very basic graphing here. But the next video will probably have more, when we talk more about the wave equation, we'll probably talk more about graphing as well. Well, yeah, okay. Well, let's get silly. Alright, so basics. So terminology is kind of a thing you gotta worry about here. So we'll just talk terms. First one I want to say is a cycle. Well, hold up, back up before that. Even before that. So there's two main types of. Yeah, we'll just erase all this crap. We'll still be in zero here. Two main types of simple harmonic systems that we've talked about, and that's a spring and mass system, and that is also a pendulum. I'm gonna make it a little bit wider. And right here is where they want to be. This wants to be right here. So like this is x equals 0 for the spring and mass system. This would be theta equals 0 for the pendulum. It's theta, and this gets pulled a distance over here. That's x. And there's there's other types of simple harmonic systems, but these are the two main that we've talked about thus far. And so one term is equilibrium, and that is just where they want to be. Theta equals 0, x equals 0. That's kind of the still point a little bit, And if we nudge it, so if we nudged this ball over, a little bit this way, it starts to move and it starts to oscillate about that equilibrium. Same for the spring and mass system. We move it this way a little bit, it's going to want to come back this way, and then back this way, and then back this way, and this way. It's going to oscillate back and forth. And so now we'll get cycle. So it is where it touches every point. So when we talked about circular motion, one full revolution is one full time around. But a cycle, if it starts, for the pendulum, starts here, it's going to come all the way over here and all the way back. That's one cycle. Just like if, this mass starts here and it goes this way, and it comes back to its original point, back to the other side, then finally back to its equilibrium. That's one cycle. Notice this, in the pendulum, it touches its original point twice. Here it's 3 times. That's just because it started at the in the center. Basically, it's got to touch every point that it's going to touch. So that's a cycle. Then there's your period. When we talked about circular motion, your period was the time it takes to go 1 revolution. Now the period is the time it takes to go 1 full cycle. So it's time for 1 full cycle. And then there's frequency. So frequency is really, it's kind of how many cycles in 1 second. So the units are kind of, I think we've talked about this briefly, kind of cycles per second. But really, it's 1 over seconds, which equals a hertz. So our unit is hertz. And so our frequency is related to our period, just like that. 1 over t. They are inversely related. My period goes up, my frequency goes down. My frequency goes up, my period goes down. So those are the main terms. Also frequency, we talked about angular frequency when we were doing circular motion and rotation. Omega, and it's related to regular frequency just by a factor of 2 pi. Which makes sense. If we plugged this into there, we end up with omega equals 2 pi over t, and that is kind of our general definition really there, or the change of the angle over the change in time. Okay, so that's kind of our general stuff. Yeah, I'll look at a couple graphs real quick. Yeah. Okay. So notice these graphs are position, oh, that was big, versus time. Because when we get into waves, it's going to be position versus displacement, but we'll talk about that next week. Okay. Let's do this. Make this smaller. So if we look at this graph, 1 full cycle, that's half, that's full. That's 1 full cycle. I'll do that. It's another full cycle. That's another full cycle. The reason I did 3 is because clearly 3 cycles takes 10 seconds. So if we think about that, 3 cycles in 10 seconds this is our frequency, right? Cycles per second, essentially. Hertz, so it'd be 0.3 hertz. To find our period is the time it takes to go 1 cycle. It's just this inverse 1 over f, the time it takes, which is 10 seconds, to go 1 cycle divided by 3 cycles. 3.33 seconds. Is that right? Math's hard. Brain's not all there. Yeah, 3 times 3 is 9. One other thing I forgot to mention is the amplitude. Alright, we'll come back to this in a sec. So amplitude, we say it's how much energy is in the system. So it just makes sense. Like if we got a pendulum right here, and we move it up to here. Right here, if we define our potential to be 0, I always forget what is it, U, V. There's so many variables for potential. We'll use U. Is 0. You know, you add that, you increase the gravitational potential energy, mgh, and the height is, of course, related to, like, if this was length L, this would be mg L1 minus cosine theta. Yeah. You do here, L, and it's h is this distance. Play around with that if you're not comfortable with that. But anyway, so our amplitude is related to how much energy. So for a pendulum, our amplitude, the unit of amplitude is just theta. It's how far away from the equilibrium you are. So this is our equilibrium. How far can be characterized by theta. Okay. Spring and mass system. You know, if we stretch it, how do we characterize how far it is away from its equilibrium? This is equilibrium. It's just the distance x. So in this case, units of our amplitude would be meters. And we'll talk more about that later. But it's how far away it is from the equilibrium. So if we look over here, well, first, notice how far away, what the equilibrium is. On this graph, it's centered about 0. So 0 is our equilibrium, which most graphs will be, but you can shift it up or down. They don't have to be. But if these, so if we draw a line right here, this is 2, and this is -2. We just say our amplitude is 2. And it depends on the system. Probably not 2 degrees, probably 2 meters. It could be 2 degrees. It changes. But so these are the 3 main variables, the fat variables: frequency, amplitude, and period. So I want y'all to pause the video and try to find the fat variables for this one. Pause it, and then when you unpause it, I will go over the answers. Okay, hopefully you took the time to try to figure it out. So if I look at this one, you can kind of tell it's, ooh, that's a big frequency. Well, anyways, that's not what I want to do. I want to do you. So we got 1 cycle, 2 cycle, 3 cycle, 4 cycles in 2 seconds. Again, that's a nice round number. That's why I did it, to clearly crosses the axis there. So 4 cycles and 2 seconds. 2 cycles per second. Just 2 hertz. That's our frequency. Our period is just 1 over the frequency. Just 1 over 2 equals 0.5 seconds. And then if we look tell our amplitudes about 0.5. So our amplitude 5. We'll just say meters. Simple. Okay. Here's another one you can do if you want. I'm not going to go over it. Same process again. But yeah, so that's it for the basics. Now we're going to talk about, so that was one. Now we're going to talk about vertical spring and mass systems. And this is really just a proof. It's not something you're going to use a whole lot, but I just want to show it to you. And actually, I was looking at the homework for the progress checks stuff, and they have some vertical spring and mass systems on there, but their questions were kind of weird, which is why I didn't assign any of that for homework. I can open it up if y'all want me to. In fact, I probably will go ahead and just open it up, but I won't assign anything, just so y'all can take a look. But so vertical spring and mass. So you've got something like this. Yeah, ooh, it's a straight line. Yay, oh my gosh, no way. Nerds. Okay. So let's say we've got this spring right here. So that spring's got a distance L. So we'll do this. We'll define here our coordinate system x is 0, and this point x is L, the length of the spring. Then we add some mass to it. I should just do that. I don't know why. We add some mass to it, and it's going to stretch the spring, right? So we add mass. And let's say it stretches a distance d. So now we have x is negative d, because we're defining this to be positive x hat. So x is negative d right there. Okay, so it has a new equilibrium point now, right? What we want to know is, okay, so when we were dealing with horizontal springs, you don't really have to take gravity in effect. But do we now? Well, first thing, let's find out what this distance d is. And we do that with trusty F is ma. And our force here is, we'll just do magnitude of force. Magnitude of force is kx. This is Hooke's law, remember? Hooke's law for spring, F is negative kx. Of course, these are vectors. But we're just doing magnitude here. So we'll say F is kx. And then we're looking at gravity, so its acceleration is the weight. So we have k. And the distance stretched, our x, the magnitude is just d, so we have kd is mg. So our distance is just mg over k. Makes sense, right? You know, more mass and gravity, the more weight, the further it stretches. The stiffer, the tougher the spring constant, the less it's going to give, the less it's going to be manipulated. Okay, so this makes sense. Okay, now we're going to do something here. We define x as 0 here, but that's no longer our equilibrium point. So we want to define a new set of coordinates, okay? And you can call these whatever you want. You can call them y, you can call them smiley face, poop emoji, like, yeah, it's just a variable. You can call it whatever you want. We're going to, I'll change the color here, just maybe this makes more sense. We're going to call it q. Why? Because I feel like calling it q. And we're going to define q at our new equilibrium point right here to be 0. Move this kind of over here. So here q is d, and way up here q equals d plus l. So we want to be able to relate these coordinate systems, right? And you might be able to do that right now, just kind of off your head. Fine. What I want to do is I want to look at these points right here. Q equals 0 is the same as x equals minus d. Well, if we just add d to both sides, we end up with x plus d equals 0. Well, you know what? 0 equals 0, which means q equals x plus d. Simple enough. And now we want to look at a conservation of energy. And remember, our potential energy U for spring is 1/2 kx squared, and our kinetic energy, this is a capital K, 1/2 mv squared. Really, this v is x dot, the time derivative, but it's fine, whatever. So for at any given point, you know, obviously down here, our kinetic energy is 0, but we'll just say for any given point, our total energy, 1/2 mv squared, it's 1/2 kx squared, right? Yeah. Plus, all right, we got to take gravity into account. Where do you think we should define our potential to be 0? I would say the equilibrium point. So this is our equilibrium point. So here, UG equals 0. Plus MGH. Now this H can be positive or negative, right? So you can have a negative potential energy if we stretched it down this way. It wants to go, actually that would be positive, just kidding. No, it'd be negative. Tripping balls. Anyways. Yeah, because it's going to be on both sides. Well, for Q. MG, this would be, we'll say MGX. Okay, but we want to put these in our new coordinate system, right? So this is going to be 1/2 mv squared. Again, now it's q dot plus 1/2. If we do this one further, x equals q minus d. So now we have q minus d squared plus mg q minus d. And we want to get these into terms, we kind of basically want to separate out the q's and d's, because d is a constant, q is a variable. So we're going to want velocity terms together plus our q terms together. I mean, we might have like a q squared and another q term plus constant, probably in terms of d. So we got to algebra this out. This part's just like kind of tedious, 1/2 mv squared plus 1/2 q squared minus 2qd plus d squared plus mgq, not mgg, mgq minus mgd equals 1/2 mv squared plus 1/2. Oh, I forgot the k. Whoops. Kq squared minus 1/2 cancels with the 2. KQD plus 1/2 KD squared plus MGQ minus MGD. Look at this, I feel like I messed up somewhere. Story of my life. CKQ. I don't know. So these two terms we can leave as is. Let's group. Go away. Something was supposed to cancel. Minus So we'll do, oh, I know what I did. So remember we have our expression here for D. I didn't mean to erase that. It's just mg over k. Well, we got a bunch of mg's and k's over here. So I'll say equals, this is the same, minus kq, was it mg over k? Yeah, mg over k. Plus k over 2 m squared g squared over k squared plus this stuff equals this minus mgq, because k's cancel, mgq. One of those k's cancel out, plus m squared g squared over 2k plus mgq minus mg, well, so it's plus mgq minus mg times mg over k. So m squared g squared over k. This term cancels with that term. So that was our linear q term. So this becomes, energy is 1/2 mv squared plus 1/2 kq squared. See, this is 1/2. No, this is 1/2. That's 1, so this becomes minus m squared g squared over 2k. Okay. This is our velocity term, which is the same. This is our kinetic energy, right? Look, this is the same as our potential for a spring. Potential 1/2 kx squared becomes 1/2 kq squared. And this is just the constant that we shifted by. Alright. However, this constant we can end up dropping, because we're going to do energy conservation. So anytime we analyze this problem, it's going to be our initial energy is going to be our final energy, and this constant is going to be the same on both sides. So you're going to have your kinetic plus your potential. Sorry for changing the variables. I know it was you. Whatever. Plus this constant equals your final kinetic plus your final potential plus that same constant. Those constants are going to cancel out. When will those constants not cancel out? Well, just look at the variables that are in it. If we change up the spring via spring mass or spring constant, I mean, it's going to change, but that's a completely different problem, so we don't have to worry about that. If we change our gravitational field, we would have to take this into account. Like if we were on a spaceship near Earth and we were analyzing the spring and then we kept it going and we analyzed it away from Earth, we might have to take this into account. But you're not going to do any problems like that. You're going to drop it. So for a vertical spring, your energy is 1/2 mv squared plus 1/2 kq squared. That's just the same as a horizontal spring. Well, for a vertical spring, same as a horizontal spring. So you really don't have to take gravity into effect. That's all I want to say about that. And then this last thing is just an energy relationship. And this shouldn't take too long, but it's very important. So to amplitude, we'll say this. Remember I said the amplitude is kind of the energy of the relationship. We move it a certain distance about the equilibrium. It has that amplitude now, and it's going to have some energy now. It's doing something. It's not just sitting there chilling. Okay. Yeah, we really don't. We'll do this kind of the simple, easy way. So, you got a spring mass system. X is 0 here. And we stretch it. Oh, we'll stretch it out here. And that's where we're going to let go. So that's the maximum distance from the equilibrium, and that's going to be our amplitude. And notice we didn't talk about damping or friction yet, so we're going to pretend like it's just going to, over here, it's going to go that same distance, A, and it's just not going to stop. Not drawn to scale, obviously. Those A's are different sizes. So, again, we let this be our equilibrium. We'll define potential to be 0 here. And this is going to be, so we're going to let go. It's going to speed up, but once it goes to the other side of the equilibrium, it's going to start to slow down and then come back. So our V max is going to be at equilibrium. Thus, because of, our kinetic energy is 1/2 kx squared. That's our potential energy. Our velocity is max about the equilibrium, so our kinetic energy is going to be maxed here. And all the way out here, at x equals a, our u is going to be maxed, and our v is going to be 0, so our kinetic is going to be 0. So analyzing this point over here, we have our total energy is 1/2 kx squared. And x is just the amplitude, so our total energy is 1/2 k a squared. There's a lot more to do with this, but I think I wish I knew it, could tell how long this has been going on. I didn't think to see what time. More or less, we'll stop here. But okay, looking at this, this is very simple, right? Our energy is proportional to the amplitude squared. So if I stretch this twice as far, all the way over here to 2a, my energy is going to go up by a factor of 4. We've done stuff like that before. But here's the thing. This is really important because when we get down and start talking about quantum mechanics, obviously we're not going to talk about quantum mechanics very much. But this relationship, the amplitude of a wave ends up being a probability of where we can find the particle, because there's something called the uncertainty principle. And we can't know the momentum and position at the same time. So quantum mechanics is a probabilistic theory. Probabilistic. I can't write. Probability. Probabilistic. Probabilistic theory. And the probability is equal to the amplitude. So how much energy the system has to do with how much we know, or how likely the particle is going to be in the area where we look for it. And there's obviously a lot more to that, but I just wanted y'all to know why this relationship is so important, because it is the backbone of quantum mechanics. Okay, that being said, look at the notes, look at the Albert homework, and I will open up the progress check so you can look at that, but I won't assign it for a grade or anything. Hope this was informative. Y'all stay healthy.